In the volcanic plateaus of India, a temple carved from a single mountain required the removal of 200,000 tons of solid basalt. Yet historical records suggest the entire structure was completed in less than 20 years. In the deserts of Saudi Arabia, a massive sandstone boulder stands perfectly split in two by a vertical gap so precise it appears to have been cut with a laser. And high in the Bolivian Andes, at 12,000 feet above sea level, scattered blocks of andesite lie across the landscape with edges so sharp and joints so tight they resemble components from a modern machine shop. These are not legends. They are documented archaeological sites that have been measured, studied, and analyzed for decades. Yet in each case, the methods used to achieve such precision remain incompletely explained. Tonight, we're examining three of the most confusing megalithic mysteries on Earth. Make sure to subscribe. We explore these kinds of documented anomalies every single week. Now let's begin. To understand the first mystery, we travel to the Aurangabad district of Maharashtra, India, where the landscape is defined by the Sahyadri Hills, a range of ancient volcanic mountains composed of solid basalt. While many civilizations throughout history have used stone as a medium for construction, the creators of the Ellora caves approached the mountain with a completely different philosophy. Instead of gathering materials to assemble a structure, they looked at a basalt cliffside and decided to remove everything that was not a temple. The result is the Kailasa Temple, the largest monolithic structure in the world, carved from a single continuous piece of rock. The project was commissioned in the 8th century by King Krishna I of the Rashtrakuta dynasty. According to local legend, the king fell dangerously ill and his queen prayed for his recovery, vowing to build the temple and fast until she could see its shikara, or roof finial. To fulfill this vow quickly, the architects proposed a radical method. They would start at the very top of the mountain and carve downward. This allowed the queen to see the summit of the temple within days rather than waiting years for a traditional building to rise from the ground. While the legend adds a layer of cultural context, the physical reality of the site confirms that the top-down method was indeed the strategy used for this massive undertaking. The sheer scale of the excavation is difficult to visualize without understanding the volume of material displaced. Builders had to cut 3 deep trenches into the basalt cliff to isolate a massive rectangular block of stone. From this central block, they began the painstaking process of carving out the intricate details of the temple complex. It is estimated that over 200,000 tons of volcanic rock were removed to create the courtyards, the central shrine, and the surrounding galleries. Unlike a traditional building where a mistake can be corrected by replacing a block, every cut made at Kailasa was permanent. There was no margin for error. The entire complex is part of the original mountain. The engineering logic required for vertical excavation is fundamentally different from standard architecture. Because the work progressed from the top toward the base, the builders had to have a complete 3-dimensional map of the finished temple in their minds before the first strike of a chisel. They had to account for the structural integrity of the basalt as they went deeper, ensuring that the massive weight of the upper stories and the heavy stone roof remained supported by columns that were being carved out of the lower levels. They were essentially engineering the support system while simultaneously creating the decorative elements, all while working in a confined space within the heart of the cliff. One of the most significant mysteries surrounding the Kailasa Temple is the timeline of its construction. Historical records and the sheer complexity of the carving suggest that the main structure was completed in approximately 18 to 20 years. This timeline has puzzled modern engineers and archaeologists alike. If we calculate the amount of stone removed over that period, it would mean that the workers were extracting roughly 60 tons of rock every single day, working around the clock. This pace involves not just the carving itself, but the logistical challenge of moving that much debris out of the trenches and away from the site using only manual labor and basic tools. Even with modern machinery and power tools, duplicating the precision and speed of the Kailasa excavation would be a formidable task. The basalt rock is notoriously hard and brittle, requiring constant sharpening of iron chisels. Furthermore, the temple is not a hollow shell. It is filled with life-size sculptures of elephants, intricate friezes depicting ancient epics, and complex drainage systems that are all part of the monolithic stone. The builders even carved internal bridges that connect different parts of the temple complex, all without the use of scaffolding. They simply used the uncarved rock beneath them as a natural platform as they worked their way down. The structural precision extends to the interior of the temple as well. To create the inner sanctum and the various halls, the masons had to tunnel into the center of the isolated stone block. They managed to maintain perfect symmetry and floor levels across vast distances, all while working by the light of oil lamps or reflected sunlight. They also had to plan for the monsoon season, carving a sophisticated network of rainwater channels and storage tanks into the rock to prevent the temple courtyards from flooding. These systems still function today, over 1,000 years after they were first conceived. As you move through the lower levels of the complex, the scale of the labor becomes even more apparent. The base of the temple is surrounded by a series of colossal elephants and lions, each one carved directly from the floor of the excavation. These figures appear to be holding up the entire weight of the temple, a visual representation of the strength required to maintain such a structure. The fact that these sculptures have survived centuries of exposure to the elements without significant structural failure speaks to the builders' deep understanding of the natural grain and strength of the basalt. The logistical mystery is further deepened by the lack of waste material in the immediate vicinity. When you remove 200,000 tons of rock, it creates a massive geographical footprint. Yet there are no significant mounds of basalt chips or rubble found nearby. This has led to various theories about how the debris was repurposed or moved. Some researchers suggest the waste was used to build roads or foundations for other structures in the region, but the sheer volume would have required a transportation network as efficient as the carving process itself. The precision of the carving raises another question. The temple features dozens of pillars, each one carved from the same piece of basalt as the floor, ceiling, and walls around it. These pillars are not uniform cylinders. They feature intricate decorative patterns, twisted rope motifs, and ornate capitals that required the masons to remove stone from multiple angles simultaneously. To achieve this level of detail, the workers would have needed to maintain a clear mental image of the finished product at every stage of the carving process. A single miscalculation in the removal of material could have resulted in a pillar that was too thin to support the weight above it, or decorative elements that were misaligned with the overall symmetry of the hall. The temple's layout also demonstrates an understanding of acoustics. The semi-enclosed courtyards and vaulted ceilings create unique sound properties. Experiments have shown that certain frequencies resonate within these spaces in ways that may have been intentional, designed to enhance the experience of ritual chanting or music performed during ceremonies. Another remarkable feature is the astronomical alignment of the temple. The main axis of the structure is oriented in a specific direction that corresponds with the rising sun during certain times of the year. This suggests that the builders were not only master sculptors and engineers, but also had a sophisticated understanding of celestial mechanics. The Kailasa Temple stands as a monument that blurs the line between architecture and sculpture. Every pillar, every staircase, and every ornate ceiling was once part of the same mountain peak. The builders didn't just construct a temple. They revealed it by stripping away the exterior layers of the cliffside, working from the top down in a process that required absolute precision and unwavering commitment to a vision that existed only in their minds. The fact that this was accomplished in less than 2 decades, using only hand tools and manual labor, remains one of the most significant engineering achievements in human history. Leaving the carved mountains of India, we travel to a completely different environment. Our next mystery takes us to the windswept deserts of northwestern Saudi Arabia, where a single geological formation has become one of the most photographed and debated anomalies in the world. Sunlight crests over the dunes of the Tema Oasis, striking a formation that seems to challenge the very physics of the desert. Emerging from the sand is a massive sandstone boulder, 6 meters high and 9 meters wide, standing as a singular landmark in an otherwise desolate expanse. From a distance, it appears to be a typical desert outcrop, weathered by millennia of wind and sun. But as you approach, a staggering feature comes into view. The rock is divided into two distinct halves by a vertical gap so straight and so clean that it looks like the result of a modern precision cutting tool. This is the Al-Naslaa monolith, an anomaly that has confounded geologists, archaeologists, and engineers for decades. The first thing that strikes any observer is the sheer uniformity of the split. The gap is only a few centimeters wide, and it maintains a near-perfect verticality from the top of the stone down to the very base. There is no shattering, no jagged edges, and no sign of the blunt force trauma one might expect from a natural rockfall or seismic event. Instead, the two faces of the split are flat and smooth, running in a perfectly straight line as if someone had taken a massive saw and made a single deliberate cut through the entire height of the boulder. Even more perplexing is how the two halves remain standing. Each massive section of the rock is balanced on a tiny narrowed pedestal of stone at its base, giving the impression that the monolith is hovering just inches above the desert floor. The weight distribution is so precise that despite thousands of years of exposure to wind, sandstorms, and temperature fluctuations, the two halves have remained in perfect equilibrium. While the split often dominates the conversation, the surface of the rock holds a historical record that dates back millennia. On the face of the right-hand block, there are several well-preserved petroglyphs, including an elegantly carved horse and a human figure rendered in the distinctive style of ancient Arabian rock art. These carvings are estimated to be around 4,000 years old, indicating that the Tema oasis was a significant site for ancient nomadic tribes and early settlers who moved through the region along established trade routes. The presence of this art confirms that the monolith has looked much like it does today for thousands of years, serving as a canvas and a landmark for the people who once navigated the harsh desert landscape. When scientists examine Al-Naslaa, the primary explanation for the split involves a process known as frost weathering or freeze-thaw erosion. In this scenario, a small amount of water finds its way into a pre-existing microfracture in the sandstone. When the desert temperature drops significantly at night, which it often does in this region, that water freezes and expands. The expansion exerts immense pressure on the surrounding rock. Over countless cycles of freezing and thawing, repeated night after night across thousands of years, the crack gradually widens and deepens. Eventually, the structural tension reaches a breaking point, and the rock splits along a natural plane of weakness. Because sandstone is a sedimentary rock composed of distinct layers of compressed sand grains, it is physically capable of shearing in very straight lines if the internal pressure is applied evenly along a particular bedding plane. Wind erosion also plays a significant role in the monolith's current appearance. The desert floor is a high-energy environment where wind-blown sand acts like a natural abrasive, constantly scouring the surface of exposed rock. This process, known as saltation, is most intense near the ground, where the heaviest sand grains are bounced along by the wind with considerable force. Over thousands of years, this abrasive action has eaten away at the base of the monolith, carving out the narrow pedestals that support the much larger mass above. This creates what geologists call a mushroom rock effect, where the base is significantly narrower than the top due to differential erosion rates. However, the mushroom rock phenomenon is seen in many desert environments around the world. What makes Al-Naslaa truly unique is the combination of this erosion pattern with a perfectly vertical split running through the entire height of the formation. Despite these geological explanations, the precision of the cut has led some researchers to question whether natural processes alone can account for what we see. They point to the extreme uniformity of the gap and wonder if ancient inhabitants of the region might have utilized primitive stone-cutting techniques to refine or enhance a natural crack. In this alternative view, a natural fissure may have already existed in the rock, created by tectonic stress or freeze-thaw cycles. Ancient masons, recognizing the significance of the stone as a territorial marker or sacred site, could have used abrasive cutting methods to widen and straighten the split, creating a more dramatic visual effect. We know from archaeological evidence that ancient cultures in Mesopotamia and Egypt developed sophisticated stone-cutting techniques using copper tools and abrasive sand. By creating a groove along the line of a natural crack and repeatedly dragging a copper wire or saw through the groove while applying wet sand as an abrasive, it is theoretically possible to cut through even hard stone over an extended period. However, applying such a technique to a boulder of this size, standing in the middle of a remote desert, would represent a massive investment of labor and resources. The question becomes, why would a nomadic or semi-nomadic society dedicate such effort to splitting a rock when there is no obvious practical benefit? The mystery is further compounded by the lack of significant tectonic activity in the immediate region. Usually, when a rock splits due to ground movement or seismic stress, there is some degree of lateral displacement. One side of the split shifts slightly forward, backward, or to the side compared to the other, creating a visible offset. At Al-Naslaa, however, the two halves are perfectly aligned. If you were to hypothetically push the two pieces back together, the grain of the sandstone would match up seamlessly, and even the edges of the ancient petroglyphs carved into the surface would align with almost no displacement. This suggests that whatever caused the split, whether natural or human-assisted, happened with incredible stability. The rock divided cleanly without toppling, without shifting, and without disturbing the delicate balance that keeps both halves upright on their narrow pedestals. The Teme Oasis itself provides important historical context. This region was not an isolated backwater, but a vital stop on the incense route, a network of land and sea trading paths that connected the Mediterranean world with the eastern and southern sources of valuable commodities like frankincense, myrrh, spices, and silk. Taima was significant enough to serve as the residence of Nabonidus, the last king of the Babylonian Empire, for nearly a decade in the 6th century BC. A culture capable of hosting a displaced monarch and managing the complex logistics of long-distance trade would certainly have possessed the curiosity, the tools, and the organizational capacity to interact with a prominent geological landmark. The balance of the stone is a masterclass in natural equilibrium. The two halves have remained standing for thousands of years despite their precarious positioning. If the pedestals were to weather away by just a few more inches, the center of gravity for each block would shift beyond the point of stability, and the entire formation would collapse. For now, the Al-Naslaa monolith remains in a state of arrested decay. The sandstone is hard enough to resist the erosive forces of wind and sand for centuries at a time, but soft enough to be gradually shaped by those same elements that will, eventually, lead to its destruction. Whether the split is purely the result of natural geological processes or represents a collaboration between nature and ancient human intervention, it serves as a powerful reminder of how much we are still learning about the long-term behavior of stone and the capabilities of ancient societies. The monolith stands as a silent sentinel in the Saudi desert, a perfect vertical line drawn through a landscape of shifting curves and organic forms, defying simple explanation and inviting deeper investigation. From the isolated deserts of Arabia, we travel to the opposite extreme, the high-altitude plateaus of the Bolivian Andes. Here, at over 12,000 feet above sea level, the ruins of Pumapunku present a mystery that moves beyond simple scale or precision cuts. This is a site where the engineering philosophy appears fundamentally different from anything else in the ancient world. The ruins lie within the larger Tiwanaku complex, scattered across a landscape of gray andesite and red sandstone. Unlike the rounded organic megaliths found in Europe or the massive singular blocks of Egypt, Pumapunku is defined by sharp lines, perfect right angles, and a level of geometric complexity that suggests an industrial modular approach to construction. Thousands of years ago, this was a massive platform and temple complex. Today it is a field of precisely cut blocks that look less like the work of ancient stonemasons and more like components from a modern machine shop. The most striking feature of Pumapunku is the collection of what archaeologists call H-blocks. These are large stones carved from andesite, a type of volcanic rock, shaped into forms that resemble the letter H when viewed from above. They feature uniform indentations, internal grooves, and carefully cut recesses that give the appearance of standardized, mass-produced components. What is particularly remarkable is the consistency between these blocks. Many of them appear to be near-perfect duplicates of one another, suggesting that the builders were working from precise templates or patterns. The surfaces are exceptionally flat, often polished to a mirror-like finish. The interior corners are cut with a sharpness that makes the stone look as if it were machined with power tools rather than shaped by hand percussion. This modularity implies that the temple complex was designed to be assembled like a massive three-dimensional puzzle, with individual pieces fitting together through their own weight and the precision of their joints, rather than being held in place by mortar or metal clamps. For years, the extreme accuracy of these stones led to speculation about their origin. Some theories propose that the Tiwanaku culture might have developed a form of ancient concrete, pouring a liquid stone mixture into molds to create the blocks. Others suggested the use of geopolymer technology, where powdered rock is mixed with alkaline solutions to create a material that hardens into stone. However, recent mineralogical and petrographic studies have definitively answered this question. Detailed analysis of the stone composition shows that the andesite and sandstone blocks are entirely natural. They contain the same crystal structures, mineral inclusions, and grain patterns as the bedrock found in nearby quarries. This confirms that these blocks were not poured or cast, but were instead carved from solid volcanic rock. The builders were performing feats of subtractive sculpture on a massive scale, removing material with extraordinary control to achieve the flush joints, sharp corners, and flat surfaces visible across the site. The logistics of constructing at this extreme altitude present their own set of challenges. At 12,000 feet above sea level, the oxygen content of the air is significantly reduced. This makes sustained heavy physical labor exhausting, even for individuals who are fully acclimated to high-altitude conditions. The red sandstone blocks, some of which weigh over 130 tons, were sourced from a quarry located nearly 10 miles away. The heavier andesite stones came from a site on the opposite side of Lake Titicaca, requiring transport across water and then overland across rugged treeless terrain. At this altitude, large trees suitable for use as rollers or sledge runners simply do not grow. This means that the traditional methods used by other ancient cultures to move massive stones would have been difficult or impossible to implement at Pumapunku. Researchers have proposed that the Tiwanaku likely used a combination of llama hair ropes, which are exceptionally strong, and stone-paved trackways that allowed workers to slide the blocks across prepared surfaces. The sheer manpower required would have been enormous, suggesting a highly organized society capable of mobilizing and sustaining large labor forces in a challenging environment. One of the more subtle but significant anomalies found at Pumapunku is the surface texture of certain blocks. Some of the andesite pieces feature a remarkably smooth, almost glassy finish that has been described by some researchers as vitrified, meaning it appears to have been partially melted or exposed to extreme heat. This has led to questions about what kind of process could have created such a surface. While some have speculated about high-temperature events, most geologists and archaeologists point toward the use of extremely fine abrasives and prolonged polishing. By using sand with a high silica content mixed with water and applying it through repeated rubbing motions over weeks or even months, the ancient masons could have gradually polished the stone to create a surface so smooth that it reflects light like a mirror. This level of finish would have served both an aesthetic purpose and a practical one, highlighting the precision of the joints and making the transitions between blocks nearly invisible. The internal structure of the temple platform provides further insight into the engineering sophistication of the Tiwanaku. The foundations were composed of massive sandstone slabs that created a perfectly level base for the more intricate andesite structures built on top. Within some of these foundation blocks, archaeologists have discovered T-shaped grooves and channels that were once filled with molten metal, likely bronze or copper. These metal clamps were poured directly into carved recesses in the stone, where they cooled and hardened, effectively welding adjacent blocks together. This technique provided the structure with a degree of seismic resistance, allowing it to withstand the frequent earthquakes that are common in the Andean region. The use of metal clamps also suggests that the builders understood the principles of thermal expansion and contraction, and designed the joints to accommodate slight movements without compromising the overall integrity of the structure. The precision required to create these joints is difficult to overstate. In many cases, the gap between adjacent blocks is less than a millimeter wide. When you run your hand across the surface where two stones meet, you can barely feel the transition. This level of accuracy would be challenging to achieve even with modern surveying equipment and power tools. The fact that it was accomplished at high altitude, using hand tools made from stone and copper, raises fundamental questions about the methods and techniques available to the Tiwanaku culture. While the site is now in a state of ruin, with blocks scattered across the landscape as if tossed by a giant hand, the remaining fragments tell a clear story. This was not a society that simply stacked rocks to create monuments. They engineered a system of modular architecture that relied on mathematical precision and repetition. Every groove, every socket, and every carefully cut edge was designed to receive a corresponding component, creating a unified structure that functioned almost like a mechanical assembly. The question of how the blocks were cut with such precision remains a subject of ongoing research. Traditional archaeological theory suggests the use of stone hammers and copper chisels, combined with abrasive sand. While these tools can certainly shape andesite and sandstone, the time required to achieve the level of precision seen at Pumapunku would be extraordinary. Some experimental archaeologists have attempted to replicate the cutting and polishing techniques using only tools that would have been available to the Tiwanaku. While they have been able to produce relatively flat surfaces and straight edges, achieving the degree of accuracy and the mirror-like polish found on the original blocks has proven extremely difficult and time-consuming. As we look across the scattered ruins of Pumapunku today, we are seeing the remnants of a project that was almost certainly intended to last for thousands of years. The stones were cut and placed with a level of foresight that accounted for weight distribution, pressure, and the slow shifting of the earth beneath them. Even in their fractured and displaced state, the blocks remain as a testament to what can be achieved when a civilization dedicates its collective knowledge, energy, and resources to the pursuit of structural perfection. The mystery of Pumapunku is not simply about how the stones were cut or moved. It is about the underlying engineering philosophy that guided the entire project. The builders created a system of construction that appears almost industrial in its approach, relying on standardization, modularity, and precision that would not be seen again until the modern era. From a temple carved downward out of a mountain in India, to a boulder split with laser-like precision in the Saudi desert, to a modular stone complex built at 12,000 feet in the Bolivian Andes, these three sites represent some of the most confusing achievements of the ancient world. Each one demonstrates a level of planning, precision, and engineering capability that challenges our assumptions about what was possible with the tools and knowledge available thousands of years ago. The Kailasa Temple required the removal of 200,000 tons of basalt in less than 20 years. The Al-Naslaa monolith stands as a perfect vertical split through solid sandstone, balanced on pedestals for thousands of years. And Pumapunku presents us with blocks cut so accurately they appear to have been machined. These are not mysteries we can easily dismiss or explain away. They are physical structures that continue to exist, measured and studied by researchers who remain divided on how they were accomplished. If discoveries like these fascinate you, make sure to subscribe to Mystic Gateways. We explore documented archaeological anomalies every week, examining the evidence and the questions that remain unanswered. Thanks for watching. Until next time, stay curious. The gateways are opening.